Hi, I'm Peter Vickers. I've been a philosopher of science here at Durham University now for 10 years. And the last 2 years I've been trying to write a book about the relationship between science and truth. And that's led to a book forthcoming at the end of this year, perhaps beginning of next year, called Identifying Future-Proof Science. So the idea, as you can tell from the title there, is that the book is going to try and show us how to identify future-proof science, or ask the question if that's even possible. So many people would say that that is impossible. We can't know the scientific ideas today that will still be around in 1,000 years or even 5,000 years. In fact, to many people that would seem hubristic to sort of say things that we can know about what human beings will think about the universe and their place in it so far in advance. If you think about what's happened in the last 1,000 years, there's been huge change in all different scientific fields and how we think about biology, chemistry, physics, and many other areas as well. The book argues that, in fact, we can identify lots of examples. And it starts in chapter 1 with a list of 30 examples of proposed future-proof science. They're not very ambitious examples. They're things like the water cycle. So at one time, people didn't know where the rain was really coming from or why the sky didn't run out of rain. And then something came along that was called a theory for a while, the water cycle theory. But nobody calls it a theory anymore. People just refer to the water cycle. And the reason we drop the word theory is because everybody accepts that we know what the water cycle is, and we know where the rain comes from, and we know lots of details about it as well. So the 30 examples, or examples like that, the book argues did come out of scientific activity originally, were at one time a theory, but then turned into fact. And at this stage become such hardwired facts that it's not unreasonable to say that that will still be a fact in 1,000 years. And there are many other examples like that, so the book argues. And it doesn't depend on us seeing it with our own eyes. So some of the examples are things that we've now seen with our own eyes that were one time a theory. So at one time it was a theory that the Earth rotates on its axis and orbits the sun. Nowadays, you could argue that we can actually see that happening from space. But the book argues that we knew it was a fact before we could do that. So how do we identify the examples then? The book argues that it's a mistake to try and assess the evidence for ourselves, the direct first-order evidence for many of these examples, because it's really, really hard to do that, even for an expert. So there's so much evidence for the water cycle that for an individual to try and digest all that evidence would just take too long. It's impossible to do, even for an expert. Many experts in the field actually get a lot of their ideas via trust, not because they've done the experiments themselves, but because they've read it somewhere, or because their lecturers told them it, or because it's something that they've absorbed from attending conferences and so on. That's not so dissimilar from the way that non-experts get factual knowledge, not because they've seen the thing for themselves or done the experiments themselves, but because you've read it in a trustworthy book. So the book introduces this concept of second-order evidence. This is really evidence about evidence. So let me give you an example. An example would be that if there's a really strong scientific consensus about some claim, for example, anthropogenic climate change, then that in itself is evidence that there is a huge abundance of first-order scientific evidence for anthropogenic climate change. The book argues that it's much easier to find out whether there's a really strong scientific consensus about that than it would be to try and look at all of that first-order scientific evidence for anthropogenic climate change, which can actually be really misleading, because if you go and try and find that evidence, then you'll only have time, even if you devote a couple of hours every day to it for a whole year, you'll still only be looking at a tiny fraction of the evidence. And the fraction of evidence you look at might be biased in one way or another. You're never going to be able to look at the whole abundance of evidence. That would be impossible for any individual, even one of the core experts in the field. So what can you do? You can find out whether there's a strong scientific consensus. When it comes to something that's as important as anthropogenic climate change, there have actually been plenty of studies that we can easily find on the internet that actually measure the strength of the scientific consensus. Scientists have been motivated to measure how strong the consensus is in that case. In other cases, scientists may not have been motivated to provide that second order evidence for us, so we have to try and assess the strength of the consensus for ourselves. One way we can do that is by seeing if there's genuine scientific controversy about an idea. This isn't so easy to do because if you look at anthropogenic climate change, it might seem like there's controversy about that when in fact there isn't. There's about a 97 or 98% consensus amongst the relevant scientific experts, and the sort of 2% or so of people who aren't so sure. If we look in the wrong place on the internet, it'll look like the scientific community is divided. Like there are those scientists who think that anthropogenic climate change is a fact, and there's those who don't, and it can look 50-50 sometimes, when in fact the strength of the consensus is more like 98%. So it can be quite tricky to try and measure the strength of the consensus. Still, that is much easier than trying to look directly at the first order evidence and make our minds up on that basis. For example, many of the skeptics about anthropogenic climate change would say that the Earth has been warmer than it is now in the past, which is true. They would also say that we're entering a new ice age, which is also in a sense true. Just picking out certain cherry-picked bits of evidence like that is really a misleading way to look at the whole abundance of evidence. So you can get sidetracked and you can get misled if you try and look directly at the first order evidence. But if you can find out if there's a really strong scientific consensus, then that is really good second order evidence that the claim is in fact a fact that will stay with us for 1,000 years or even 5,000 years. There are a few caveats that need to be added. One is that we want the community, the scientific community involved, to be large, we want it to be diverse, and we want it to be international. Those three things make it more difficult for a consensus to emerge just for the wrong reasons. So because of a bandwagon effect, for example, or some other fallacy of reasoning. If you have a really large scientific community and it's got a sufficient diversity of perspectives, then people on one side of the world will be very quick to assess and criticize what's being said on the other side of the world. In science, there is this culture of trying to show that other people are wrong. When there is that culture in place, it means that when a consensus does emerge, that's something that's really important and really worth taking notice of. So to sum up, the book is arguing that if you have a consensus which is strong, and I argue that 95% consensus is strong enough, so if 95% of the relevant community agree that it's a fact, then that's strong enough. And if the relevant community is international, large and diverse, then you can be sure that the idea in question is future-proof. Now, why can you be sure about that? Well, the book argues that there are many, many examples where those criteria have been met, and there's never been an example which met those criteria and then was later rejected. And that's despite enormous opportunity for that to happen if it were ever going to happen. So why has there been such enormous opportunity for that to happen? One reason is that some of the things that were initially posited are now actually observable because we've developed new techniques, we've developed new instruments. Take continental drift, for example. Continental drift was hugely controversial between about 1915 and 1960. Then, during the 1960s and 70s, a consensus started to emerge, and that consensus reached a stage of being about 95%, somewhere around the 1980s or 1990s. It doesn't matter exactly where, but it certainly meets my criteria for future-proof science at that stage. But since then, we've developed techniques for actually observing continental drift happening. And that observation of continental drift by GPS satellites and so on confirms what was already known back in the 80s and 90s, that continental drift was and is a fact. So we've had these opportunities for these facts to be overturned if they were ever going to be. And one of the important ways in which that happens is when we develop techniques at a later time via which the claim in question can be assessed by observation. Not exactly direct observation with the naked eye, but observation that counts as observation to the scientific community in question, such as seeing drift happen with those GPS satellites. If the book is right, that the best way to identify future-proof science is to assess the strength of the scientific consensus, if a consensus exists, that's something that's quite challenging to do, and especially because none of us are taught how to do that during our school education. So in school educations across the world, there's no effort made to teach people, to teach students how to assess second-order evidence for scientific claims. Some effort is made in how to assess first-order evidence. Students are, of course, taught about science. They're taught how to use a microscope, how to use a Bunsen burner. They're taught about the periodic table, but none of that helps them to assess the second-order evidence. How do we work out how strong a scientific consensus is? Who are the relevant scientists? Which sources on the internet are going to be reliable sources when we try to work out the strength of the consensus? All of these things are very tricky to do. The book goes through various examples trying to show how to do that. One of the key examples in modern times is the theory of the asteroid impact as the cause of the extinction of the dinosaurs. So I go through that example showing how we can measure the strength of the scientific consensus regarding that theory. If we want people to be able to identify scientific facts, the facts that are going to last forever, not just soft facts that are sometimes just said to be facts for now, then we do want in our schools to teach some of those skills to the students. So thank you very much. I hope you enjoy the book, and I'd love to get any feedback on the book if you have any.